So, in solving problems, we are going to look at a particular methodology which I have just listed here. So, we are going to find out whether there are one or more systems or control volumes, whether we can deal with the substance considering it to be a system, or do we need to consider it to be a control volume which is more suitable. We will then identify any energy transfers across the boundary in the form of either work or in the form of heat. For this, we may also need to find out what are all the forces acting on the system, so that we can find out work or any work interactions which are there. We will need to list out what we know about the initial state before the process happens. So, what do we know about the initial state? Do we know the temperatures? Do we know the pressures? Do we know volumes or energies or enthalpies, or what else do we know? And the fourth point brings us to the thermodynamic model, and this is where we are going to discuss for the time being. So, what is the property relation? So, are temperature and volume connected in some way? Are pressure and volume connected in some way? Is the internal energy connected to temperature or pressure or volume or any other form? So, once we know this, then we can go to the rest of it. So, we are going to now look at the property relation, and we will come back to this problem solving methodology to solve problems once we figure out what these property relations are. This brings us to the question of what is an ideal gas. So, this is something which most of us have studied at some point in school. So, we have some answer to this already. So, we say that any gas can be treated as an ideal gas if molecules exert negligible attractive forces on each other. So, the molecules are not going to affect each other, and this assumption is valid if the molecules are separated and they are sufficiently far apart so that there are no attractive forces, which means that the molecules are far apart, which means the volume of this gas must be very large, which means that the specific volume is very large. So, we can think of it in the limit of specific volume going towards infinity, which would happen if the pressure is extremely small, so that the molecules are far apart. And in that case, what we can assume is that these gases follow the Boyle's law, which tell us that the pressure into volume is constant if the temperature of the gas is constant. So, if it undergoes an isothermal process, then if it follows this kind of a relation, we could consider it to be an ideal gas. It also has to follow the Charles law, which tells us that the volume and temperature are related when the pressure is constant. So, what we see is that the volume is proportional to the temperature when pressure is constant. This is another thing it has to follow, and putting these two together, we get essentially this expression. So, if the gas follows this kind of an expression which shows the relation between the properties, if the pressure into the volume divided by temperature is constant, then we would call this an ideal gas. And this would happen if the molecules are separated out and there is no attractive forces between individual molecules. So, putting them all together, we get an expression of this kind. We get PV is equal to some N into some R bar into T, where we have N is the number of moles, R bar is the gas universal gas constant, which we often also indicate by the RU, R subscript U, to indicate it is a universal gas constant. N is the number of moles, T is the temperature. We are going to use the SI unit. So, Kelvin is our unit for temperature. P is the pressure. We are going to use SI units again. So, the units are either pascals or kilopascals. V is volume. Our unit is meter cube. So, we have this. These are our units. Now, the question is, what is the unit of the number of moles? So, defining all of the other things in this fashion, our unit we are going to use for number of moles is essentially a kilomole. Okay. In schools, often you would have used moles, and we are going to use a kilomole as the unit here, which gives us the units for R. So, pressure has units of pascals, volume has units of meter cube, pressure into volume has units of work, which is the unit of joule, and we have, so R has units of PV by N, so that is joule per kilomole, and divided by T, so that is joules per kilomole Kelvin, and this value turns out to be about 8314.5 in joules per kilomole Kelvin. So, this is essentially the value which we are going to use. So, this expression is correct if the quantity of gas which we have is given in kilomoles or moles. So, we know that from Avogadro's law, we know how many molecules there are in a mole. We also know what is the volume occupied by a mole at standard temperature and pressure and so on, which is turns out to be about 22.4 liters. But it is not a particularly useful unit for the kind of calculations we are going to do, because we do not have a very good understanding of how much the volume is at some other pressure and temperature. So, for example, at atmospheric temperature, let us say I know the volume is a certain thing. I do not know how much the volume is at, say, when the temperature is, say, 200 degrees centigrade. So, what is a more useful unit for us generally is to look at these things in terms of mass, because I know, for example, that this phone has a certain mass. I know that if I change the temperature, the mass still is the same, and that is something which I can sort of feel. I can sort of have it in my hand and give you some estimate of it. Let us say I can say it is about 200 grams or 100 grams or something like that. So, that is a more useful unit for us. So, the more useful expression for us is essentially the second expression here, which says PV is equal to M into R into T, where P is still the pressure with the same units as earlier, V is the volume, same units as earlier, but now I am going to have mass, which is M, which our unit in SI units is kg, and then I have T, which is in Kelvin. So, in this case the R is what we call as the specific gas constant, and this is what we are going to usually use, and the units of this are going to be pressure into volume, which is joule, divided by M, which is in kg, and divided by T, which is in Kelvin. So, this is going to have units of joule per kg Kelvin. In contrast to this, what we have on top over here is what we of course call as the universal gas constant. So, the reason we call the first one as universal gas constant is that it is the same irrespective of what gas we have. If we have hydrogen, the universal gas constant is still 8314.5 joule per kilomole Kelvin. If it is oxygen or nitrogen, it is still the same, whereas the specific gas constant depends on what gas we have. So, this value would be different for, like, say, nitrogen, different for, say, oxygen and so on, but irrespective of that, this is usually a more useful way for us to look at things. So, we are going to usually keep using this. We can also write this expression in different forms. So, we can, for example, if you take this first expression over here, that was PV is equal to N into universal gas constant into T, I can divide by N here, then I get pressure into V by N, which is what we call as the specific molar volume, which is in contrast to the specific volume, which is what we divide, which we have defined in this fashion. So, this is what we call a specific volume when we divide the volume by the mass, whereas if we divide the volume by the number of moles, we usually indicate it with a bar on top, and this is what we call as a specific molar volume. And so, we can also get this expression, pressure into specific molar volume is universal gas constant into temperature, or we can use this expression and divide by M here, then we get P into V by M is RT, or P into specific volume is RT, which in writing normally I would write the V in this fashion, which is another expression which we are going to use quite a lot. Or we can take this V to the other side and we get P is equal to 1 by V into RT, and 1 by V is essentially the density. So, it would give us an expression of this form, which is again something which we can use. But in doing all of this, what we are yet to see is the relation between this part. So, we said that over here R is a specific gas constant. So, if we look at the comparison, so essentially what we see is that the specific gas constant is the universal gas constant divided by the molecular mass of the gas which we are looking at. So, R bar has the same value and the molecular mass is different of course for different gases. So, if you are looking at say for nitrogen, so then we know that the molecular mass or molecular weight as it is more often called is we know that it is about 28 kg per kilomole. So, if you are looking at hydrogen it is say 2 kg per kilomole and so on. So, if we divide R bar by that, we get by the molecular mass or molecular weight, then we get R over here, which is what we are going to generally do.